Hello, my name is Andy Nguyen. Today I'm going to talk about our work, efficient out-of-memory sparse MTTKRP on massively parallel architectures. This is a joint collaboration between University of Oregon, Intel Labs, and Laboratory for Physical Sciences. As an overview of our talk, I will first discuss sparse tensors and introduce what they are. I'll then talk about the sparse tensor kernel MTTKRP, which is the focus of our work. I will talk about prior city approaches to accelerating this kernel, and then I'll discuss our approach, which includes a new tensor data format, a new parallel algorithm, and then some empirical evaluations. Let's get started. A tensor is a multidimensional array. So in the one-dimensional case, we have a vector analogous to an array. When we add another dimension, we get a 2D array or a matrix. And then when we add more and more dimensions, we get tensors, which are generalizations of matrices and high-dimensional arrays. Tensors capture real-world data. For example, you can express product review information for a recommendation system using a tensor, or you could express, say, electronic health records for representing patients' medical data in a tensor, or even law enforcement data you can capture using tensors. So it's important that we study tensors and accelerate their algorithms and come up with efficient data formats so that we can accelerate these real-world applications of it. A sparse tensor is a tensor where most of its elements are actually zero. And so in a sparse tensor, it's only important to keep track of the non-zero elements, which in this example is expressed in blue. One way to do that is by creating a table where you keep track of the indices along each dimension and then the associated value for each point. So each row in this table corresponds to a single non-zero point in the high dimensional space. This format is called the coordinate format. It's analogous to the coordinate format for matrices or for sparse matrices. However, sparse tensor kernels are even harder to optimize than sparse matrix kernels for a number of reasons. For one, there's decursive dimensionality. What this means is essentially as you go into higher and higher dimensional space, points tend to get farther and farther apart from each other. The sparsity tends to increase. And so this makes it tricky to study sparsity patterns and scale the higher dimensions. And on top of that, you have algorithm scalability, meaning it is difficult to scale to higher dimensions without adding increased time complexity to algorithms. And these two in tandem also make it difficult to compress high dimensional data, especially when it is sparse. Now, one application of tensors is tensor decomposition. Here is a diagram of the canonical Polyadic decomposition for CPD. You approximate a tensor as a sum of these low rank or rank 1 tensors. And so not only does this compress the original tensor, but this allows you to sort of extract the most salient features of the original tensor by breaking it up into important factors. So this is a useful tool for data analysis and data mining. Now, when computing a CPD, one of the main bottlenecks is matrix-sized tensor times Cauchy-Rao product, or MTTKRP. And so I have the formal notation for this kernel on screen, and on the right here is a diagram of an on-the-fly implementation of this kernel. Essentially, you fetch rows from the various factor matrices, you combine them together with Hadamard product, and scale by a non-zero value from the input tensor, and then you finally accumulate to some output factor matrix. Now, accelerating this kernel has a number of challenges. For one, this is very memory intensive kernel. A lot of the data is coming from the factor matrices, and so it's important to efficiently fetch data from these factor matrices. There's also the issue of complex data locality. This is in part because of the sparsity of the tensor. This requires us to optimize how we use caches and things like data locality in order to optimize MTTKRP. There's also synchronization overhead when updating factor matrices. When we implement this kernel in parallel, updating this factor matrix causes a lot of contention and overhead. And so managing that is a difficulty. On top of that, there's the issue of load imbalance across threads. When you have a parallel implementation of MTTKRP, you need to efficiently load balance in order to achieve maximal performance. And yet another issue is when you're implementing MTTKRP on GPUs and GPU accelerators, and that is the focus of this work. GPUs have limited memory, which can cause out-of-memory issues when you have extreme scale tensors. And so figuring out how to manage that memory and compute on such out-of-memory tensors is yet another issue of MTTKRP. So let's talk about how prior state-of-the-art approaches solve this problem. State-of-the-art approaches generally have an optimized tensor data format that they operate on in order to accelerate MTTKRP. So on the far left here, we just have the coordinate format. It's analogous to the coordinate format for matrices. Here in the middle, we have flagged coordinate. It is similar to the coordinate format, except for one particular mode, the indices are replaced with these bit flags and start flags. These flags indicate the changes in the mode, and these flags allow for an implementation of segmented scan in order to merge intermediate results and update factor matrices more efficiently. So this is a list-based format. It retains each individual non-zero element along with their indices, and this structure or this data format is built so that a segmented scan can be made possible. However, it requires a mode-specific representation, since these bit flags and start flags only work for mode. For the first mode, you would need additional bit flags and start flags for the other modes as well. Here we have mixed mode CSF. This is the current state of the art, and it is a tree-based format. Rather than storing each individual non-zero element individually, elements with matching indices in a particular mode are grouped together. So for example, for this tree here with 4, this includes all the non-zero elements with 4 as its index from mode 1. Mixed mode CSF is an implementation is a improvement over CSF, which is a tree, which is also a tree-based structure. Mixed mode CSF is essentially a forest of trees, where each tree is potentially stored in a different mode orientation. This is to both improve data compression while retaining the minimized synchronization updates required, thanks to the tree structure. Now, there are some problems with the current state-of-the-art, which is mixed mode CSF. Here, we've measured the performance of mixed mode CSF on certain tensors, and we're looking at every individual mode separately. And so these bars are normalized against the best performing mode, and so higher is worse in this case. So in some cases, depending on what mode you are, you're very close to the optimal execution time, but on certain modes, the performance degrades drastically. In the worst case, we actually observe over an order of magnitude worse performance, depending on the mode. It's important to note that all modes require the same number of flops. And it's also important to note that when performing MTTKRP in a CPD implementation, we must do MTTKRP against every single mode. And so the drastic performance variations drag performance down overall. Here's a quick summary of some prior state-of-the-art implementations. We talked about flagged coordinate and mixed mode CSF, and while I won't go over all the details of this table, the big takeaway is that these state-of-the-art approaches have various trade-offs that severely impact performance. There's currently not an implementation that sort of gets the best of all worlds simultaneously. So to that end, we turn to our work, our data format called blocked linearized coordinates. or BLCO for short. This is a list space, yet highly compressed and massively parallel tensor format. BLCO has a number of features, including index linearization, which maps the multidimensional coordinates into linear space. It has adaptive blocking, which blocks the tensor to meet target GPU resource constraints, namely in memory. And we also introduce a hierarchical conflict resolution algorithm, which resolves the synchronization conflicts in MTTKRP using all levels of the memory hierarchy. So let's start with index linearization. This means that element indices are linearized into one-dimensional space. So in this example diagram, the non-zero elements in the tensor are mapped to the number line. And instead of keeping track of 3 separate indices for each non-zero element, you only keep track of a single index. This has a number of performance benefits. For one, this is a highly compressed representation. You only need to keep track of the single index on the number line instead of 3 separate indices, or the index or equal to the number of dimensions. Another benefit is this makes more effective use of memory bandwidth. Essentially, by compressing all the indices into a single index, we are using a higher percentage of the bits of that index. And so we're essentially using a higher percentage of what the memory subsystem actually sends us. By keeping the format as a list-based format, this still allows for fine-grained parallelism, since each element can be processed individually and independently. This allows us to achieve optimal load balancing. Now, the elements are first linearized and ordered based on prior work alto. And here is a depiction of that. Essentially, the bits from each mode are interleaved together, and all the non-zero elements are sorted based on the resulting index. Following that, after reordering, we then relinearize the indices to group or concatenate the bits back together so that each mode bits are consecutive rather than interleaved. And this allows for fast delinearization on GPUs. Now, one problem this introduces is that the resulting linearization may actually exceed the integer width. For example, 64 bits. In this example, the original linearization has 6 bits, but here you're only storing 5 of them. And so our solution to this is to block the resulting linearized tensor based on the excessive bits. In this case, there's only 1 excessive bit, so there's only 2 blocks generated at most. Blocking like this has a number of performance benefits. For one, this is a mode agnostic approach. I showed earlier that chart where there was performance variation depending on the mode in the current state-of-the-art implementation. And so by keeping this format mode agnostic, we are able to have more consistent performance across the various modes. This adds minimal memory overhead since we're not storing additional information at the per element level, but instead at a higher block level. And an important feature of this is that blocks can actually be streamed in for out-of-memory computation. What this means is that each block can be independently processed. And so when we're dealing with an out-of-memory tensor, an extreme scale tensor, which may not even fit on the limited memory of a GPU, we can actually stream in the individual blocks of that tensor and process them independently during an execution of MTTKRP. This allows us to stream in a tensor and execute on it in order to deal with those out-of-memory tensors. So this is something that no other framework has been able to achieve. And finally, since the elements are still stored in this list space format, we are able to expose fine-grained parallel processing by simply exposing fine-grained parallelism within a block. Now, when we're updating the factor matrix in MTTKRP, this introduces synchronization overhead, which is generally expensive for list-based formats since you need a write for each non-zero element. And this is especially true for GPUs since GPUs have quite a lot of threads and each may potentially contend with one another for writing to that output factor matrix. So our solution to this is to leverage the various memory levels of the memory hierarchy in order to minimize global atomic writes. Here I have a diagram of the of a typical memory hierarchy of the GPU. There is global memory and then some number of caches, and then there's a separate shared memory that can be manually managed, and then there's register level memory. And so our algorithm works as follows. At the register memory level, we implement segmented scan to merge intermediate results together. At the shared memory level, we implement a software controlled cache in order to store output rows from rows that are commonly written to. And then at the global memory level, we implement a pull-based reduction to merge all the results from all the thread blocks and partial matrices into the final output matrix. In more detail, our MTTKRP implementation looks like this. Each thread within a warp of the GPU first fetches and delinearizes each non-zero element. So the fetch comes from the global memory and then is delinearized in shared memory. And then the threads are partitioned into tiles, and then the non-zero elements within each tile are reordered. There are segmented flags generated in order to assist with the segmented scan and reordering. And all this happens in register level memory and stored to shared memory. Following this, we reassign the threads from being per element to being per output to perform the rank-wise update. And so the MTTKRP calculation happens, or update happens in register level memory, and then this then gets accumulated to the software controlled cache in shared memory. And then once all that is finished and everything gets written to global memory, all the various partial factor matrices get merged together by a pull-based reduction at the global memory level. So in summary, with our new data format and this new algorithm, we are able to make very little compromise and achieve performance on a number of ways, from load balancing to efficient synchronization, and while still maintaining a mode agnostic format that only needs a single copy to represent the entire tensor. Let's take a look at some experiments. So the GPUs we use for this are the latest Intel discrete GPU, as well as the two latest NVIDIA cards, the A100 and B100. Here we're comparing against 4 state-of-the-art frameworks in total: mixed mode CSF, flagged coordinate, Gen 10, and an RWork BLCO. Our data sets include 14 real-world tensors from the Frost repository, and we compile in double precision with 64-bit data types. All right, this first experiment is an overall framework comparison. So we're comparing our work BLCO against 3 others, most notably mixed mode CSF, which is the current state of the art. So all of these are speed up charts, and they're all normalized against mixed mode CSF. So mixed mode CSF in red is always at 1.0. And on the right here, we have the various GPUs that we measured on. And you can see across the board, there is speed up on every device and on every tensor. On average, we achieved 2.6x speed up over the prior state of the art. This is happening on the NVIDIA A100 card. And also to note that we observe speed up across the various architectures. What this means, what this suggests is that our data format is actually architecture agnostic. And you can see similar speed up regardless of the architecture. Let's take a closer look at comparing against the current state of the art, mixed mode CSF. Here we have another speed up chart normalized against the current state of the art. However, we're looking at individual modes for MTTKRP execution instead of the all, or like an all mode MTTKRP. And so what we find is on the smallest of tensors, the tensors are ordered from least number of non-zeros to most number of non-zeros from left to right. So on the leftmost tensors, we do find there is measurable slowdown compared to the current state of the art. This is expected because mixed mode CSF is a tree-based structure. And so they're able to compress their tensor representation more than our own format. So for the smallest tensors, their factor matrices can actually fit entirely in cache. What this means is that the most efficient way to get speed up is simply by reducing the amount of data fetched. And that is something the current state of the art excels at compared to our own. As the number of non-zeros increases, when we move to the right, we can see on these largest of tensors, we are getting consistently better performance. Let's take an even more in-depth look at GPU performance counters to study memory traffic. We're comparing our format against the current tree-based state-of-the-art. And we're looking at some select tensors and we're measuring the total volume of memory fetched from global memory. And then we're also measuring the throughput achieved of that memory traffic. And so what we find is the current state-of-the-art mixed mode CSF achieves a lower memory traffic overall. This is because they are a more compressed tree-based data structure. So this is not surprising to us. But what we also observe is when we look at the throughput numbers, our BLCO format actually achieves higher memory throughput. And this is thanks to our hierarchical conflict resolution, where we use every level of memory. And it's also important to note that BLCO has less performance irregularity across the different modes. Depending on what mode you are performing MTTKRP on, for mixed mode CSF, performance might either be great or it might drastically degrade, whereas we have much more consistent performance across the board. Now, here we have charts analyzing our out-of-memory tensor performance. Now, no other framework can handle these out-of-memory tensors that don't fit in GPU memory, and so we cannot compare against other frameworks. We can only compare against ourselves. And so what we're comparing here is the memory throughput of our data structure and our memory throughput when we do not include any data exchange, where we do not consider any host device memory interactions. What we find is our theoretical performance when we ignore the host device data exchange is actually on par with the in-memory tensors. The memory throughput we achieve here is up to speed with the memory traffic analysis table I showed you on the previous slides. However, we don't actually achieve such high throughput. Our realized throughput turns out is actually being throttled by the hardware interconnect bandwidth. So what this means is while our support for out-of-memory tensors is theoretically on par with in-memory tensors, we're being limited by our hardware configuration. Here we're analyzing the cost of constructing the BLCO format. BLCO can be thought of as an extension over the prior work Alto. And so here we have various stages of constructing BLCO. The first three stages are for constructing the Alto data format, and then BLCO adds some additional overhead to the Alto data format. What we find is BLCO generally does not take too much overhead over Alto to construct. At worst, it's only less than 25% of the overall cost or time to construct the format. So there's not much overhead to construct the BLCO format. When comparing again, so BLCO has minimal overhead over the Alto data format. When we compare against other frameworks, what we find is BLCO will always cost more than Alto. This chart is measuring execution time to construct the tensor format for various tensors. So BLCO is always going to add overhead over Alto, but the overhead is typically very minimal. And more importantly, it's much faster than the other state-of-the-art frameworks, most notably the current state-of-the-art mixed mode CSF in red. So BLCO is consistently faster to construct than any other framework. Now, to close off this presentation, tensors are becoming prevalent for data analysis. Therefore, efficient tensor formats and algorithms are needed to maximize hardware utilization and throughput. Our BLCO format that I introduced outperforms the current state-of-the-art by up to 33.35 times speedup, average 2.60, through novel data compression and massively parallel computation. And our future work includes exploring heterogeneous shared memory computation and extension to distributed memory platforms. Thank you.